Hi, my name is Muhammad Hadi. This is project 3 of Electrical Engineering 2 EI4. The date of this recording is the 29th of March 2025. So this is the schematic of my circuit. So as you can see, my chosen transistor was a BJT. Specifically, as you can see right here, the 2N3904, simply because this was the model that we were provided in our project kit. And yeah, I wanted to use a BJT rather than a MOSFET because we do have some prior experience using a MOSFET from project 2, and I wanted to try something different for this project. And honestly, the BJT seemed more simpler and easier to use as per the project requirements. So moving on, the BJT is known for better linearity and also having a higher GM value that a MOSFET just simply won't be able to provide. The BJT is also the BJT also performs better in low current applications, and also is faster and good for low voltage and power applications. So these are the three topologies: the common emitter, the common base, and the common collector. The topology I chose for this project is the common collector. This is because it seemed the most simple. I'm pretty sure all the topologies are doable for this project. I didn't really look into it, but yeah, the most simplest one was the common collector, which is why I chose it. And yeah, like some of the reasons I chose it were because the common collector, as per this formula sheet, gives a gain of about 1, which is what we're looking for. We need a gain of like about 1, like a little bit less than 1, so this would be good for that. And yeah, basically all these different topologies are good for different applications. Like for example, the common emitter would be good for like amplification based projects. The common base would be good for it would be suited for like current buffer, and the common collector, which is what we chose, would be good for like unity voltage gain applications, which is what we're trying to do in this project. In addition to this, the common collector has a high input resistance, which means the current won't interfere with the voltage, and the current will overall stay preserved. So now let me show you my calculations for each of the component. I screenshotted this from my iPad, so that's why the resolution isn't that good. But yeah, so this formula I took from the formula sheet. VFT is 25 millivolts, the load resistor is 100 ohms, and VI is 0.5 volts. And yeah, so I just plugged in these values into this formula, and I just simplified, and yeah, GM. So the answer GM is equal to or greater than 990 millisiemens. And this is the calculation I used to find Rn. And as you can see, the gain, the AV value is greater than 0.9. The load resistor is 100 ohm, and RS is 100 ohm. So yeah, same as the last one. I just plugged in these values accordingly and simplified, and found Rn, which is equal to greater than 1 kilo ohm. For the capacitor, I just used it was just trial and error, but like just for simplicity, I used the 100 nanofarad, and it ended up working. So like I was fine with it. I didn't really like do anything. It was an arbitrary value, and for R1 and R2, that was arbitrary too. The values didn't really from what I saw, the values didn't really have an effect on Rn. So yeah, I just ended up using 10K for both of them. So from the previous calculation, it tells us that Rn must be equal to or greater than 1 kilo ohm, and so we're trying to do here, we're trying to calculate Rn. So the formula for Rn is R1 parallel to R2 parallel to Rn, and we chose for R1 and R2 we chose 10 kilo ohm, and Rn it was missing, so that's what we calculated here. So as per the formula sheet, like I got these equations from the formula sheet. So yeah, Rn is equal to R pi times 1 plus Gm times RL, and R pi is essentially equal to Rs over Gm. So I just plugged that into R pi, and I just plugged in some of the values I got. I did some simplifying, and Rn prime is equal to 10.1 kilo ohm, and then I plugged that into here. I simplified this, and I found that Rn is equal to 3.34, which meets the requirement, meets the requirement of the inequality that Rn must be equal to or greater than 1 kilo ohm. Let me just go through my circuit. So yeah, let me just go through my schematic. If you like, let me start from the left side. So yeah, we begin with a source voltage of sinusoidal wave. This is the inputs, offset 0, amplitude 0.5, and a frequency of 10,000. Yeah, this is where I calculate the input voltage, and as you can see, we're hit with the 100 ohm resistor, which connects to a 100 nanofarad capacitor, and then at this node there are two 10k resistors, both which are parallel, and they both connect to ground. And then we are at the base of the BJT. Then on the collector there is a input voltage of 5, and that connects to ground. And then at the emitter there is a node 1 which connects to a load resistor of 100 ohm, and that connects to a negative 5 voltage which connects to ground. And then the other side of the node connects to 100 nanofarad, and this was supposed to connect to the ground. However, I was having difficulties running my simulation, like it wasn't working. I did some research, and I found out that if I connect the output to a really high kilo ohm resistor, and then I connect it to ground, like that would help. I really don't understand why, but like I found out that LT Spice doesn't really like open circuits, so like you should just put a really high resistor to make it almost open. And yeah, that like fixed my issue. So the transient analysis was performed on this simulation. As you can see, the stop time value I chose was 0.001. If I run this simulation, you can see, let me just plot the voltage and the current. Yeah, so as you can see with this stop time, I found this to be the perfect number, because as you can see, it's very easy to analyze. The oscillation amount is perfect. Like let me show you what I mean. So if it was a little bit higher, like let's say, oh no, one second. Say if it was 0.01, as you can see, there would be way too many oscillations, and it would not be that easy to analyze. And if the number was lowered, then I guess you could still analyze it, but I just preference, I wouldn't like it like this. So yeah, that's what I see this as a perfect number. So when I run my simulation, this is going to be the output graph. As you can see, the green is the input voltage, the blue is the output voltage, and the red is the input current. And one thing you notice from this is that the output and input voltage are like practically like very similar, they're very aligned, which does prove linearity. And one more thing is, like the phase shift difference in the input current is because basically I like when I was measuring my circuit, uh, I measured the input backwards. So yeah, like it's basically in reverse. So yeah, that would explain that. But yeah, anyways, the output voltage is 466 millivolts. The input voltage is 400, basically 500 millivolts, and the input current is one sec. It would be equal to 119 picoamps. So in order to calculate the gain, the formula for that would be VO over Vn, which the output voltage we got from this graph was 466, and if you divide that by about 500 millivolts, that would mean that the gain is about 0.932, which meets our design specifications of the gain being over 0.9. And in order to calculate the Rin, which is the input resistance, the formula for that would be Vin over the input resistance. So that would be about about 4.2 kilo ohm, which is good. It's relatively close to the input resistance we calculated by hand. Now it's important to know that like some of the values we get won't be exactly accurate or like exactly the right answer, but the calculation is relatively close to the measured value, to the value we got. So yeah, that should be good. Hi, so this is my physical circuit. It's connected to the 82 right now. As you can see, it's like everything's powered on. But yeah, this is my circuit. So it starts right here. This yellow wire right here is the sinusoidal wave. Yeah, the orange wire is the V inputs. It's connected to positive channel 1. It's connected to the 100 ohm resistor, which is also connected to this like blue this blue thing is the 100 nanofarad capacitor. It looks different because I got it from somewhere else, so it's not from campus. But yeah, it's this 100 ohm resistor connected to the 100 nanofarad capacitor, and in the same node is the two 10k resistors right here. It puts in the same node as the capacitor. The two resistors are, as you can see, they're both connected to ground in parallel. And also in the same node as the capacitor and the two 10k ohm resistors is this green wire, which you can see right here. It's connected to the base of the BJT, so that's the base. Yeah, so yeah, that this, and as you can see right here, this node is the collector of the BJT, and it's connected to this red wire here, which is connected to it's connected to the 5 plus 5 positive voltage. So yeah, that takes care of the collector side of the BJT and the base side. So like moving on, now we're at the emitter side, which as you can see, it's connected to the same node as the 100 nanofarad capacitor and the 100 ohm resistor. So yeah, they both like go to separate nodes. So the capacitor is like you can see this this blue wire is equal to positive channel 2, and that is what the other side of the capacitor is equal to, and the 100 ohm, it's equal to, it's in the same node as this green wire, which is equal to basically a -5 voltage from the 82. And yeah, if like finally, if you look right here, this is like the this is like simply the ground. It's the black wire connected to 82 ground. And this orange wire is positive channel, no, negative channel 2, and this white wire is negative channel 1. So this is my waveforms for the previously shown circuit for scope 1 and scope 2. So orange is V in, the V in, and blue is the V output. And immediately looking at this, you can see that like both the V in and V out are like practically identical. Like they're very similar. Like for the most part, they're like overlapping each other, which is one way of proving linearity. There are two other ways that I will show in a bit, but first, here are the measurement values. You can see, like, I don't know why, for some reason it wasn't letting me change the C2 to voltage, but like it was in but yeah, like you can see, yeah, they're pretty similar. So yeah, the C1 C2 maximum, C1 C2 peak to peak, and C1 C2 frequency, and then the M1, which is the match channel, and this is C2 over C1, which, like we all know, is the V output over V input, which is just calculating the gain. So over here the gain is 0.97, and that is well within the project requirements, so everything checks out here. And yeah, let me just run it. So as you can see, everything looks fine. Okay, so moving on, one way to find the mid-band gain and as well as linearity is we would go over to the wave gen and like tweak around, play with the amplitude, see if anything changes. So yeah, let's just try two different values. So for the what we saw before was with 500. Let's try 200. Okay, 200, and oh my bad. Yeah, 200. Okay, as you can see, all the this channel 1, channel 2 values are still pretty consistent with one another. Yeah, still like pretty similar, and the average, the gain is still pretty much the same. It's over 0.9, which like meets the project consideration, the project requirement, and yeah, it's still over 0.9. You know, everything looks okay. And let's try one more value. Wave gen. Let's just try 100. Let's do the same thing. Go to scope, and yeah, as you can see, maximum values are pretty consistent with one another, peak to peak frequency, and the gain is still over 0.9, and yeah, it hasn't really changed throughout us tweaking the amplitude. Still stayed pretty much like this, the same as 500, and yeah, one more way, like if you move on, like I'm sorry, I kept going to the spectrum by accident because I thought I got mixed up between scope, but this is the spectrum. We run it. Yeah, as you can see, like the values are like for both voltages, like the values are like very similar. Like if we zoom in, which is what I did here, you can see that like they basically follow each other. Like if one goes one direction, then the other goes in a similar direction. So yeah, it's like pretty consistent, which is another. And yeah, this shows that the strength of V1, no, my bad. The strength of V in and V out are like practically like very similar to each other. And yeah, this this is good for us. It proves that the design meets the project requirements, it meets the project specification, and yeah.